Light is the first language of the universe. Long before life existed to see it, before atoms joined into stars, light filled the newborn cosmos as a sea of energy expanding in all directions. Every observation we make today, from the glow of the sun to the faint afterimage of the Big Bang, is translated through this same medium. Without light, there would be no astronomy, no sense of distance, no knowledge of the universe beyond the reach of our hands. What we call light is a small part of a vast electromagnetic spectrum, a continuum of waves and particles that carry energy across space. The part visible to our eyes, the rainbow from red to violet, spans only a tiny range of all possible frequencies. Beyond violet, light continues as ultraviolet rays, X-rays, and gamma rays, each more energetic than the last. Beyond red, it stretches into infrared, microwaves, and radio waves, carrying lower energies but still belonging to the same electromagnetic family. If we could see the entire spectrum, the universe would appear unimaginably different. The night sky would blaze with invisible forms of radiation. Cold clouds of hydrogen would glow in radio light. Dying stars would shine in X-rays. Even the Earth's surface would hum with infrared energy, revealing the hidden heat of every living thing. Yet our eyes evolved only for the narrow band of light most abundant from our sun. To us, the world seems complete, but we are perceiving only a sliver of reality. Electromagnetic radiation is a self-propagating oscillation of electric and magnetic fields. These fields generate one another as they travel, allowing light to move through empty space without a medium. This was one of the most revolutionary discoveries of the 19th century, that the vacuum itself can sustain waves of energy. When James Clerk Maxwell unified the laws of electricity and magnetism, his equations predicted that these waves would travel at a constant speed. When he calculated that speed, it matched the known speed of light almost exactly. From that moment, it became clear that light is an electromagnetic phenomenon. The smallest indivisible unit of this radiation is the photon, a quantum of light energy. It behaves as both wave and particle, depending on how it interacts with matter. When it strikes a metal surface, it can knock electrons free, as seen in the photoelectric effect. When it passes through a narrow slit, it interferes with itself, forming patterns of alternating brightness. This dual nature is not a flaw in description, but a fundamental truth about how energy behaves at the smallest scales. Our relationship with light is not just scientific, but existential. Everything we know about the cosmos, from the closest planet to the most distant galaxy, is known because light has carried information across space. It travels in straight lines, unless bent by gravity or matter, and along the way, it records the properties of everything it touches. Through light, we can measure temperature, composition, motion, and distance, often with astonishing precision. The key to this knowledge lies in the technique of spectroscopy. When light from a star passes through a prism or a diffraction grating, it spreads into a spectrum of colors marked by dark or bright lines. Each element leaves a unique pattern, determined by the energies of its atomic transitions. By comparing these patterns to laboratory measurements, astronomers can determine what distant stars are made of, how hot they are, and how fast they move. This same principle allows us to identify the atmosphere of a planet orbiting another star, or to measure the rate at which galaxies recede from us. Even the simplest beam of light carries a record of its journey. As it moves through space, its wavelength can stretch or compress depending on the relative motion between source and observer. When an object moves away, the light waves are stretched, shifting toward the red end of the spectrum, a phenomenon called redshift. When it moves toward us, the waves compress, creating blue shift. By measuring these shifts, astronomers discovered that distant galaxies are moving away in all directions, revealing that the universe is expanding. To look deeper into space is to look back in time. Light does not reach us instantaneously. It travels at a finite speed, about 300,000 kilometers per second. so every observation is a glimpse of the past. The light from the sun takes about 8 minutes to reach Earth. The light from the nearest star takes more than 4 years. When we observe the Andromeda galaxy, we see it as it was more than 2 million years ago. When telescopes capture the faint glow of the cosmic microwave background, they reveal the universe as it existed almost 14 billion years in the past. Every photon that reaches us carries the story of an ancient event. Some were born in the cores of stars, others in violent explosions called supernovae. Some have traveled untouched through the emptiness of intergalactic space, while others have been scattered, absorbed, or re-emitted countless times. The universe we see is a tapestry woven from their paths. Yet light also hides as much as it reveals. Most of the universe is invisible to any form of electromagnetic observation. Ordinary matter, the atoms that make up stars, planets, and living beings, accounts for only a small fraction of the total cosmic energy budget. The rest is dark matter and dark energy, detectable only by their gravitational influence. They neither emit nor absorb light, remaining beyond direct observation. Thus, while light allows us to see, it also defines the limits of sight. Every photograph of the cosmos, no matter how deep or detailed, is shaped by what light chooses to show us. Between the bright galaxies lie vast voids filled with unseen structures. Even within our own galaxy, dust clouds obscure the starlight behind them, hiding regions where new suns are born. The development of infrared and radio telescopes has lifted parts of this veil, revealing forms and motions once unimaginable. But each new window we open only reminds us that we still perceive the universe through light's selective filter. Still, the study of light remains our best tool for understanding the nature of reality. By tracing how it moves, how it bends, and how it interacts with matter, we uncover the structure of the cosmos itself. It is not merely illumination. It is the very geometry of perception. Every coordinate we assign in space, every measure of time, every physical constant is calibrated against it. And from this dependence on light emerges a profound truth. Light does not merely travel through space and time, it defines them. The constancy of its speed shapes the universe's deepest architecture, binding together energy, motion, and causality. To follow light wherever it leads is to trace the outline of reality itself, a journey that will carry us from the visible world into the fabric of space-time and perhaps beyond. From the moment scientists began to question the nature of light, they found themselves standing at the edge of a deeper mystery, one that connected perception, measurement, and the structure of reality. The story of light's constancy was not discovered in an instant, but through a series of experiments that gradually revealed how the universe behaves at its most fundamental level. For centuries, thinkers believed that light, like sound, required a medium through which to travel. They called this invisible substance the ether, a hypothetical ocean filling all of space, carrying the vibrations of light waves. It was believed to be perfectly transparent, without mass or resistance, and at rest relative to the universe itself. The ether was thought to be as real as air or water, its stillness providing the stage upon which light could perform its motion. In the late 19th century, physicists began testing this idea with increasing precision. If Earth were moving through such a medium, then the speed of light should vary depending on direction. Just as the speed of a boat depends on whether it moves with or against the current. Albert Michelson and Edward Morley built an instrument of astonishing sensitivity called an interferometer, designed to measure these differences. By splitting a beam of light into two perpendicular paths and then recombining them, they could detect even the tiniest changes in its travel time. Their result, published in 1887, shocked the scientific world. No matter how they rotated their instrument or when they performed the experiment, the outcome was the same. The speed of light did not change. It was identical in every direction, unaffected by Earth's motion around the sun. This failure to detect the ether was more than a puzzling null result. It was a clue that nature might not require a medium at all. The idea that light needed no carrier was difficult to accept. Many tried to save the ether hypothesis by proposing that it was dragged along by Earth, or that measuring instruments contracted when moving through it. These explanations grew increasingly contrived, while the evidence for light's constancy remained firm. A new idea was needed, one that could explain not only why light's speed stayed the same, but why all observers, regardless of their motion, would measure that same speed. In 1905, a young clerk working at the Swiss Patent Office published a paper that transformed physics. Albert Einstein began with two simple postulates. The first stated that the laws of physics are the same for all observers moving at constant velocity. No frame of reference is privileged. The second declared that the speed of light in a vacuum is the same for all observers, no matter how fast they move relative to the source. These statements, taken together, forced a radical rethinking of space and time themselves. If light's speed is constant, then time and distance cannot be absolute. They must adjust so that this constancy remains true. A moving clock runs slower relative to a stationary observer, and a moving object shortens in the direction of motion. These effects are not illusions or measurement errors. They are woven into the fabric of space-time. The faster something moves, the more these effects grow, until at light speed, time stops and length shrinks to zero. This realization changed everything. The old Newtonian universe, with its rigid separation between space and time, was replaced by a new geometry in which both were intertwined. Space could stretch, time could dilate, and the two together formed a four-dimensional continuum. Light did not simply move through this continuum, it defined its very structure. The fixed speed of light became the cosmic ruler by which all motion and measurement are compared. Over the next century, experiment after experiment confirmed these predictions. Muons, created in Earth's upper atmosphere, live longer than they should because they travel near light speed. Atomic clocks aboard aircraft and satellites tick at slightly different rates depending on their velocity and position in Earth's gravitational field. The global positioning system must account for both special and general relativistic effects, or its navigation would drift by several kilometers each day. Einstein's equations revealed another astonishing truth. Energy and mass are equivalent. A small amount of mass corresponds to an enormous amount of energy, multiplied by the square of the speed of light. This relationship, written as energy equals mass times the speed of light squared, underpins both the burning of stars and the operation of nuclear reactors. The sun shines because hydrogen nuclei fuse into helium, converting a fraction of their mass into radiant energy carried outward by photons. Light's constancy is thus not a trivial curiosity. It is the foundation upon which modern physics stands. It governs not only motion and time, but also the balance between matter and energy. Without this constant, the equations describing electromagnetism, gravity, and quantum theory would fall apart. At the deepest level, the speed of light defines the limit of causality, the maximum rate at which information or influence can travel. No signal, no interaction, can propagate faster without violating the order of cause and effect. This limit is not arbitrary. It emerges naturally from the geometry of space-time itself. When we say that nothing can travel faster than light, we are not merely setting a speed limit. We are acknowledging that light defines the boundary of possible experience. The constancy of this speed gives rise to one of the universe's most elegant symmetries. The equations that describe physics remain unchanged for all observers moving at constant velocity because the speed of light provides a universal reference that replaces the old notion of absolute space and time. Everything that exists, every particle, every field, every force, must conform to this underlying geometry. But light's story does not end here. Its constancy reveals more than the nature of motion. It exposes the connection between the observable universe and the deeper structure of reality. If time slows for things that move close to light speed, then what happens to something that always travels at that speed? How does the universe appear from the perspective of light itself? To explore this question is to cross a threshold from the world of matter into the realm of the massless, a place where distance and duration lose their meaning. The answer lies in understanding the photon, the elementary quantum of light, whose existence challenges our everyday intuitions about space and time. For a photon, there is no waiting, no before and after. It is born, and it arrives in the same instant, a connection between two events that, from its own frame, have no separation in time. This is not a poetic statement, but a consequence of the mathematics of relativity. The photon travels at the cosmic limit, the one constant speed that defines the structure of space-time itself. According to Einstein's equations, time slows down as velocity increases. At light speed, time ceases to pass entirely. The concept of duration becomes meaningless. When we imagine a photon leaving the surface of the Sun and reaching Earth 8 minutes later, that time interval is true only for us, the observers who are at rest relative to the journey. For the photon, those 8 minutes vanish. The emission from the solar surface and the absorption by our eyes or instruments are a single event. Light, in this sense, does not experience travel. It does not age. Every photon we detect today was created at some moment in the past, yet from the photon's perspective, that creation and detection happen simultaneously. This peculiar behavior forces us to see time not as a universal flow, but as something woven differently for every observer. In our daily lives, time appears absolute because we move slowly compared to the speed of light. But in the equations of physics, there is no single clock ticking for the universe. Each observer carries their own measure of duration, and only light defines the invariant boundary that connects them all. The constancy of light speed means that space and time are not separate fabrics, but one continuous structure, space-time, whose geometry bends and stretches depending on energy and motion. Light not only travels through this geometry, it defines it. Every pulse of radiation traces the shortest possible path between two events in space-time, a path known as a geodesic. When space-time is flat, these paths are straight lines. When mass and energy warp the fabric, light bends accordingly, curving around stars, galaxies, or entire clusters. This is not because gravity pulls on light as if it had mass, but because light always follows the straightest possible route through curved space. The bending of starlight around the Sun, first confirmed during the solar eclipse of 1919, provided one of the earliest direct proofs of Einstein's general theory of relativity. Photographs of the eclipse showed that stars near the darkened edge of the Sun appeared slightly displaced from their usual positions, exactly matching the predicted curvature. That simple observation revealed that gravity is not a force acting through space. It is the geometry of space itself. And light, by following that geometry, allows us to see its shape. Modern telescopes have turned this principle into one of the most powerful tools in astronomy. When a massive object, such as a galaxy cluster, lies between us and a more distant source, its gravity bends the light from behind, magnifying and distorting the background image. This phenomenon, known as gravitational lensing, has allowed astronomers to map the distribution of dark matter. Matter that cannot be seen directly, but whose gravity reveals its presence. Through light's deflection, we have discovered invisible structures extending across millions of light years. At the most extreme limit of curvature lies the black hole, a region where space and time are so distorted that nothing, not even light, can escape once it crosses a boundary called the event horizon. Here, the geometry of space-time becomes vertical. All paths, even those of light, lead inward. Yet light still defines the edge of this abyss. The event horizon is, by definition, the surface where the escape velocity equals the speed of light. In 2019, the Event Horizon Telescope captured the first direct image of such a region. the shadow of the black hole in the galaxy Messier 87. The glowing ring surrounding the dark core is light bent by gravity, tracing the edge where photons orbit the black hole before, spiraling inward or escaping outward. That image was not an artist's impression, but a direct measurement of light obeying the laws of relativity in one of the most extreme environments known. Through such observations, we have learned that light is more than a messenger. It is a probe into the nature of existence itself. Its constancy connects energy, mass, and geometry. Its curvature reveals the shape of space. Its absence marks the boundaries of the known universe. Every photon carries information not only about where it came from, but also about the structure of the cosmos through which it has traveled. Yet light also points toward the limits of our understanding. If time stands still for the photon, then what does that mean for the deeper nature of reality? Does the universe, from light's perspective, exist as a single timeless whole? The mathematics does not allow us to assign a viewpoint to something moving at light speed, but it tempts us with questions about what lies beyond space-time as we perceive it. Physicists have long sought to extend these insights, to understand how light, gravity, and quantum mechanics fit within a single framework. When Einstein unified space and time, he gave us relativity. When Maxwell unified electricity and magnetism, he gave us electromagnetism. The next great step, the unification of all forces, requires an even broader view, one that may demand additional dimensions of space beyond the familiar three. The path forward, as always, begins with light. Its constancy, its quantum nature, and its interaction with gravity are the clues leading toward the next layer of understanding. Just as light revealed the geometry of space-time, it now hints that the universe's deeper architecture may extend beyond our visible dimensions. The journey that began with the question of what light is now leads to the profound question of what reality itself is made of. The universe operates according to rules that appear unchanging, woven into the very mathematics that describe it. At the heart of these rules lies a single number, the speed of light in a vacuum, which serves as the ultimate constant of nature. It does not matter who measures it or how fast the observer moves. The result is always the same. This is not simply a statement about light, but a statement about the structure of existence itself. The constancy of this speed defines the connection between space and time, and it establishes the limits within which all events unfold. Before this was known, physicists believed that the world behaved according to Newton's absolutes. Space and time were separate, rigid, and universal. Clocks ticked at the same rate everywhere. The speed of a moving object depended on how it was measured relative to the observer. It seemed natural to assume that light should follow the same pattern. If Earth moved through space, then the speed of light should appear different depending on whether one measured it along or against Earth's motion. But nature refused to cooperate with this expectation. In the late 19th century, Michelson and Morley sought to detect these variations using their precision interferometer. They reasoned that as Earth orbited the Sun, it must be moving through the invisible ether that supposedly filled space. Light moving in the direction of this motion would take longer to return to its source than light moving at right angles to it. When the beams were recombined, any difference in speed would shift their interference pattern. But the shift never appeared. No matter how carefully they measured, the speed of light remained unchanged. This was one of the most important null results in scientific history. It meant that either the ether did not exist, or the rules of motion were profoundly different from what anyone imagined. Some physicists tried to preserve the ether idea by proposing that moving objects physically contracted as they passed through it, an ad hoc solution with no independent evidence. Others suggested that the ether somehow moved with Earth, though this required an implausible degree of fine-tuning. It was Albert Einstein who saw that the simplest explanation required abandoning the ether altogether. In 1905, he proposed two postulates that formed the foundation of special relativity. The first was that the laws of physics are the same for all observers moving at constant velocity. The second was that the speed of light in a vacuum is the same for all such observers, regardless of their motion or the motion of the light source. These two principles, taken together, implied that space and time themselves must change depending on the observer, so that the speed of light remains invariant for all. From these ideas came a revolution: time dilation, the slowing of clocks in motion, and length contraction, the shortening of moving objects along. The direction of travel are not illusions, but real, measurable effects. The faster an object moves, the more pronounced these effects become. As it approaches the speed of light, its passage through time slows almost to a halt. Were it to reach that ultimate speed, time for it would stop altogether. The experiments confirming these predictions are numerous and decisive. Subatomic particles known as muons, created in the upper atmosphere, decay after only a few millionths of a second when at rest. Yet those traveling close to the speed of light live long enough to reach detectors at Earth's surface. This is not because their internal processes have changed, but because time itself flows differently for them relative to us. Atomic clocks flown around the world and compared with identical ones on the ground show precisely the same difference predicted by Einstein's equations. Even the satellites orbiting Earth must account for these effects, or the global positioning system would lose accuracy by several kilometers each day. Einstein also uncovered a relationship between mass and energy so simple that it could be written in a single line. Energy equals mass, multiplied by the square of the speed of light. This equation revealed that mass is not a separate substance, but a concentrated form of energy. The enormous factor of the speed of light squared means that even a small amount of mass contains a vast store of energy. This principle powers the stars, whose nuclear fusion converts tiny amounts of mass into radiant light and heat, sustaining life across the cosmos. To call the speed of light a constant is to recognize it as the boundary between what can happen and what cannot. No signal, no particle with mass, can reach or exceed it. The energy required would grow without limit, and the geometry of space-time would forbid the attempt. In this way, light defines causality, the relationship between cause and effect. If one event could influence another faster than light could travel between them, the order of events could reverse, destroying the consistency of the universe. The constancy of light speed therefore becomes the organizing principle of space-time. In Einstein's framework, the separation between two events is not measured solely in space or in time, but in a combination of both. This quantity, known as the space-time interval, remains the same for all observers, even though they may disagree about individual distances or durations. The speed of light is the conversion factor that binds these quantities together. 1 second of time corresponds to about 300,000 kilometers of space. The invariance of this relationship ensures that all laws of physics remain consistent in every reference frame. This redefinition of the universe had profound consequences. Space and time were no longer fixed backdrops against which events occurred. They were dynamic and interwoven, bending and stretching in response to motion and energy. The geometry of space-time is such that light always moves along the same type of path, regardless of the observer's speed. That path represents the limit of what is physically possible. Light, therefore, is not simply a phenomenon moving through the cosmos. It is the metric by which the cosmos measures itself. To test this idea further, physicists built ever more precise instruments. Lasers, interferometers, and atomic clocks have confirmed the constancy of light to astonishing precision, varying by less than 1 part in 10 to the power of 17. Even the arrival times of gamma rays from distant cosmic explosions, traveling billions of years across expanding space, show no measurable difference in speed across different energies. These results strengthen a simple but profound truth. The speed of light is not just a property of light itself, it is a property of space-time. This constant binds together the entire physical universe. It connects the smallest quantum processes to the largest cosmic structures. It allows energy to transform into matter and matter back into energy, linking the birth of stars, the decay of particles, and the ticking of every clock in existence. It defines how information moves, how forces interact, and how time flows. Light is therefore the great harmonizer of nature. Through its invariance, the laws of motion, electromagnetism, and gravity coexist without contradiction. Every experiment, every observation, confirms its role as the cornerstone of reality. The more deeply scientists probe the universe, the more they find that this constant is not merely about how fast something moves. It is about why the universe holds together in a coherent, intelligible form. And yet, even this constancy opens new mysteries. Why should the universe possess a finite maximum speed? Why does this single value emerge so naturally from the equations that govern energy and geometry? These questions lead directly to the nature of the photon, the particle of light itself, and what it means to exist at this ultimate boundary. The deeper scientists explored the constancy of light, the more they realized it was not simply a coincidence of nature, but a reflection of something fundamental about reality. The speed of light is not just how fast electromagnetic radiation moves. It is the maximum rate at which information, energy, or causality can travel. In a sense, it is the cosmic speed of logic itself, the rate at which the universe updates its own events. To understand this constant is to understand the very rhythm by which existence unfolds. Einstein's insights transformed this idea from speculation into measurable fact. Time and space were no longer separate quantities. They were interwoven dimensions that adjust relative to one another, so that the speed of light remains the same for every observer. In this unified fabric, distances and durations depend on perspective. To one traveler, a journey might take years. To another moving faster, it may pass in moments. Yet the light connecting them both traces an identical path through space-time, unaltered by motion or perspective. To grasp how strange this is, imagine two observers, one standing still, the other moving near light speed. Each shines a beam of light forward and measures its speed. Classical intuition says that the moving observer's light should seem faster, since motion adds to the light's velocity. But nature disagrees. Both observers measure exactly the same speed, 300,000 kilometers per second, no matter how they move. The universe compensates by adjusting their experience of time and space so that the result remains invariant. Time slows for the moving observer, and distances contract, preserving light's constant speed. These effects are more than theoretical curiosities. They shape everything from the functioning of particle accelerators to the lifespan of cosmic rays. When scientists accelerate electrons in circular rings close to light speed, their masses appear to increase dramatically. It becomes harder and harder to push them faster, because as they gain energy, space-time itself resists, stretching the rules of motion to keep light's limit intact. This is why no particle with mass can ever reach the speed of light. It would require infinite energy, and infinity is something nature does not permit. This fundamental limit also governs the structure of cause and effect. In the geometry of space-time, every event is surrounded by a region called a light cone, the zone that light can reach moving outward from that event. Anything inside the cone can be influenced by it. Anything outside cannot, because signals cannot travel faster than light. This simple geometric rule prevents paradoxes in which causes might follow their effects. It is the reason the universe has a consistent arrow of time. If information could travel faster than light, events could occur out of order depending on the observer's motion, making cause and effect meaningless. Light's constancy preserves causality, ensuring that the sequence of events remains the same for everyone. Even the most distant galaxies follow this law. When we see their ancient light, we are not witnessing them as they are, but as they were billions of years ago, bound to us by the finite speed that defines the flow of time itself. The constancy of light speed also ties together energy and matter through the equation. Energy equals mass multiplied by the square of the speed of light. This formula is not just symbolic, it quantifies the unity between mass and energy. The immense factor of the speed of light squared means that even a small amount of matter contains a colossal amount of energy. When atoms fuse inside the cores of stars, tiny fractions of their mass vanish, transformed into radiant light and heat. Every sunrise on Earth is powered by this equation, its brilliance a direct expression of the relationship between mass and energy. This same principle underlies the most powerful technologies humans have ever built. In nuclear reactors and atomic bombs, the conversion of matter into energy follows Einstein's rule with exact precision. Yet nature herself has been performing this process for billions of years, in every star that burns and every supernova that explodes. The constancy of light ensures that these processes are not chaotic, but predictable, following the same laws in every corner of the cosmos. Even at the cosmic scale, light's role as a universal constant guides our understanding of the expanding universe. When astronomers measure how the wavelengths of light stretch as galaxies move away, they use the redshift of light as a cosmic yardstick. The expansion of space itself changes how we perceive time and distance, yet the local speed of light remains fixed. This constancy allows cosmologists to reconstruct the history of the universe with remarkable precision, tracing its growth from the first flash of the Big Bang to the galaxies forming today. Every test devised by modern science has confirmed the invariance of light speed. Measurements of distant gamma-ray bursts, traveling for billions of years across the universe, reveal no deviation. The energy of a photon, whether high or low, does not affect how fast it moves. Experiments on Earth using laser interferometers show that even as the planet spins and orbits the Sun, the speed of light never wavers. Within the limits of measurement, better than 1 part in 10 to the power of 17, it remains the same. This remarkable stability reveals something profound. The universe is not arbitrary. It operates according to symmetries that give rise to conservation laws. The constancy of light is linked to the symmetry of space-time itself. Because the laws of physics are the same for all observers moving uniformly, certain quantities, like energy and momentum, remain conserved. The invariance of light speed is the physical manifestation of that deeper harmony. But perhaps the most fascinating consequence of light's constancy is that it points toward unity among the forces of nature. The same equations that describe light's behavior also hint at the relationship between electromagnetism and gravity, between quantum particles and curved space-time. These connections suggest that the speed of light may not only define how fast something moves, but how the universe is structured at every level. If the speed of light is the conversion factor between energy and mass, between space and time, then it is not just a constant within the universe. It is the defining property of the universe. To understand its origin is to seek the foundation of all physical law, and to follow this constant to its limits leads to the very edge of physics itself, where light's nature as both wave and particle merges with the fabric of space-time. The next step in this journey is to examine what it means to move at light speed, not as a thought experiment, but through the photon itself. The photon, massless and timeless, travels across the universe as the pure embodiment of this constant. Through its behavior, we can glimpse the geometry of the cosmos and the possibility that motion, time, and existence are far more interconnected than we ever imagined. For the photon, the universe unfolds in a way that no human can experience. From our perspective, light takes time to cross distance, but for the photon, distance and time vanish. In the equations of relativity, the proper time of a photon, the time measured in its own frame, is 0. This means that a photon emitted from a distant star and one absorbed by a telescope billions of years later are connected by an event that, for the photon, is instantaneous. Its journey, no matter how vast, happens in no time at all. This idea may seem impossible to picture, because our brains are anchored in a world where time always flows forward. Every heartbeat, every sunrise, every orbit of Earth defines a rhythm we call duration. But light lives beyond that rhythm. It exists at the boundary where time ceases to pass. To understand why, we must look again at what makes the photon unique among all particles. The photon is massless. It has no rest frame, no way to slow down, and no lower speed than the constant of the universe. This is not a trivial property, but a direct result of the symmetry that governs electromagnetism. In the language of quantum field theory, the electromagnetic field possesses a kind of mathematical balance called gauge invariance. This symmetry requires that its carrier, the photon, must be massless. If the photon had even a tiny mass, the laws of electromagnetism would change, and the infinite reach of light would collapse to a finite distance. The long-range nature of light is therefore proof that this symmetry holds perfectly. Because photons lack mass, they are unaffected by the passage of time in the way matter is. They cannot rest, because rest would require a reference frame where they exist with zero velocity, which relativity forbids. Their very existence is defined by motion. The photon is not something that moves through space. It is the movement itself, the pure transfer of electromagnetic energy. This realization reshapes how we think about both space and time. In the geometry of space-time, every particle traces a path called a world line, a record of its history through the universe. For massive objects like planets or people, these world lines curve gently through both space and time. For light, the path is different. It lies exactly on the boundary between all possible motion and the impossible. The photon's world line is not inside the light cone or outside it, but along its surface, where time and distance blend into one. Light's timelessness has extraordinary consequences. Because it never experiences time, a photon can carry information across the cosmos without aging or changing its intrinsic nature. The light we detect from a distant galaxy has traveled for billions of years, yet the photon that enters our telescope is exactly as it was when it began its journey. It has crossed expanding space, curved around massive objects, and endured the stretching of wavelengths caused by the universe's growth. Yet for the photon, none of this took any time at all. In this sense, light is the perfect historian of the universe. It records events as they happen, then delivers them to us untouched by time's passage. Every photon from the cosmic microwave background carries the story of the universe's first few 100,000 years, frozen in a signal that has not aged since it was released. When we observe that faint radiation, we are not just seeing into the past. We are directly encountering ancient light that, from its own perspective, has only just left its source. This property makes light the ultimate mediator between matter and energy. It communicates changes in electric and magnetic fields, allowing atoms to interact, molecules to form, and stars to shine. It carries the energy that fuels photosynthesis, the radiation that warms planets, and the information that allows us to observe the cosmos. In every case, the photon plays the same role, a timeless messenger bridging space and matter. Yet the photon is also the boundary marker of reality's deepest structure. Because it moves at the speed of light, it sets the limit beyond which no causal influence can pass. This limit defines the universe's causal structure, the network of all possible interactions that can occur. It is through this structure that physicists build models of how energy, matter, and space relate. Remove the photon, and causality itself loses definition. The constancy of light thus serves as the spine of physical law. Every field equation, from electromagnetism to gravity, aligns with this invariant speed. Even in quantum mechanics, where probabilities rule, the propagation of information through light's finite speed ensures that no effect can occur before its cause. The universe's consistency, its refusal to allow contradictions in time or energy, depends on this single constant. But the photon also carries us to the edge of what current physics can explain. When we combine the mathematics of quantum mechanics, which governs the very small, with general relativity, which governs the very large, contradictions appear. Light behaves as both a wave and a particle, as continuous and discrete. Its motion defines space-time, yet space-time curves in response to the energy that light itself carries. This mutual dependence hints at a deeper framework, one that unites all forces under a single theory. That search for unification leads to a remarkable possibility. Perhaps the universe needs more than the 4 dimensions we experience to remain mathematically consistent. When scientists attempted to combine gravity, electromagnetism, and the quantum behavior of light, they found that the equations worked only if extraspatial dimensions were introduced. These hidden dimensions may be compact, curled up so tightly that they escape detection. Yet their existence could explain why light and gravity behave as they do. Thus, the constant speed of light does more than shape space and time. It may point toward dimensions beyond them. The very fact that light defines space-time structure might mean it also defines how that structure extends into deeper, unseen layers of reality. The quest to understand these layers has driven physics for the past century, from the first unification attempts of the early 20th century to the modern theories that describe a universe of 10 or even 11 dimensions. And so, as we follow light further, we find that it is not only the key to seeing the universe, but the key to understanding its hidden architecture. The next step in our journey is to explore how the effort to merge light, gravity, and quantum mechanics inevitably led physicists to the idea of higher dimensions. A concept born not from speculation, but from the mathematics of the very constant that defines reality. Light does not merely illuminate the universe, it defines it. Every second, countless photons cross the cosmos, carrying energy and information from one point in space-time to another. Yet for the photon itself, that journey is instantaneous. In our frame, a photon may take billions of years to travel from the edge of the observable universe to reach a telescope on Earth. But from the photon's perspective, there is no time between emission and absorption. The beginning and the end of its existence are one and the same. To understand how this can be true, we must return to the mathematics of relativity. The rate at which time flows depends on an object's velocity relative to the speed of light. As that velocity approaches light speed, time for the object slows down. For massive particles, time always moves forward, though it slows with speed. For a photon, however, which has no mass, the flow of time ceases altogether. Its proper time, the time measured by a clock moving with the photon, is zero. This concept is difficult for the human mind to grasp because our entire perception of existence is built on the experience of duration. Every process we know, the beating of a heart, the orbit of a planet, the aging of a star, unfolds through the passage of time. Yet the photon exists outside that flow. It is the bridge between one moment and another, connecting cause and effect without itself experiencing the interval between them. This timeless nature of light has profound implications. It means that when we detect light from a distant star, we are receiving something that, in its own frame of reference, never aged. That photon was emitted from a nuclear reaction in the star's core long before human civilization existed. Yet for the photon, the event of its creation and its arrival here are the same point in its own reality. The universe's age, expansion, and evolution all happen from our perspective, not from light's. The photon's motion also challenges how we think about space. To us, distance separates objects, but for the photon, traveling at the universal constant, distance collapses. Between its origin and destination, there is no spatial separation, only a single event. In this sense, photons exist everywhere along their paths at once. They connect regions of space-time in a way that transcends the usual limits of location. This is not just philosophy, it is measurable in physics. Experiments confirm that light behaves as if it knows the entire path it will take. In the double-slit experiment, when photons pass through two narrow openings and strike a screen, they form an interference pattern, a signature of waves overlapping. Even when photons are sent one at a time, the pattern still emerges over time, as though each photon travels through both slits simultaneously and interferes with itself. If we try to measure which slit the photon passes through, the interference vanishes, replaced by a simple pattern of particles. This strange duality, wave and particle, lies at the heart of quantum mechanics. Light can behave like a particle, delivering energy in discrete packets, yet also like a wave, spreading out and interfering across space. The photon is neither and both. It does not choose a path until it interacts with something that forces a decision. Until then, it exists in a state of probability, described by a mathematical wave function that encodes all possible outcomes. Richard Feynman, one of the great interpreters of quantum electrodynamics, described this behavior through the principle of path integrals. In his view, a photon explores every possible path between 2 points, and each path contributes to the probability of where it will be found. Most of these paths cancel out, leaving only those that correspond to the familiar straight-line motion we observe. What we call a photon's path is the result of an immense sum over all possibilities, a kind of cosmic negotiation between probability and geometry. Even in this probabilistic framework, the photon still respects relativity's constraints. None of its possible paths allow it to exceed the speed of light. Its timelessness does not mean it moves infinitely fast. Rather, it means that motion at light speed erases the concept of time altogether. To the photon, the universe's dimensions collapse into a single continuum of connections, with no distinction between now and then, here and there. This interplay between quantum behavior and relativity reveals the photon's unique role in physics. It is the fundamental mediator of the electromagnetic force, carrying the interactions that bind atoms and allow chemical reactions. It is also the vehicle by which information travels across the cosmos. Everything we know, from the color of a leaf to the spectrum of a galaxy, is conveyed through photons. They are both the messengers and the message. When we consider light this way, we realize that it is not merely an occupant of space-time, but one of its defining elements. The photon does not move through space. It generates the connections that make space meaningful. The geometry of the universe is written in the language of light. Without it, the concepts of distance and duration would lose their physical meaning. And yet, as perfect as the photon seems, it also exposes the limits of our theories. Relativity treats light as continuous, while quantum mechanics treats it as discrete. When we attempt to merge these views, contradictions arise. The smooth curvature of space-time clashes with the granular nature of quantum fields. Somewhere beyond our current understanding, these two descriptions must converge. Physicists have long suspected that this convergence may require new dimensions, not metaphorical dimensions of thought, but literal extensions of space beyond the three we experience. The mathematics of unifying light with gravity and the other forces leads naturally to this idea. If space has more dimensions than we can perceive, they may be compact, curled up so tightly that they remain invisible to current experiments. Yet, their presence could explain why light behaves as it does and why its speed remains constant. This possibility first emerged in the early 20th century, when theorists attempted to unify Einstein's equations of general relativity with Maxwell's equations of electromagnetism. By adding just one extra spatial dimension, they found that both forces could be described as aspects of a single geometric framework. This elegant approach, known as the Kaluza-Klein theory, suggested that higher dimensions are not speculative imagination, but a natural consequence of combining light and gravity. Through the photon, we are thus led to the threshold of a larger universe, one in which the familiar dimensions of space and time may be only part of a grander structure. Light, as the one entity that transcends both, becomes the key to understanding that structure. From the earliest efforts to merge the great forces of nature, light has served as both a guide and a constraint. Its behavior is so fundamental that any successful theory of the universe must reproduce it exactly. When gravity and electromagnetism are expressed in geometric form, light emerges as the common thread between them. Yet when physicists first attempted to bring these two realms together, they discovered that the mathematics pointed towards something extraordinary. The universe might require more than the 4 dimensions we observe. The first step in this realization came in the 1920s with the work of Theodore Kaluza. He extended Einstein's general theory of relativity by adding one extra spatial dimension. In this 5-dimensional spacetime, the equations of gravity naturally produced not only the familiar curvature that accounts for gravitation, but also an additional set of terms that mirrored the equations of electromagnetism. Kaluza's insight suggested that the two forces could be manifestations of a single underlying geometry. A few years later, Oscar Klein refined the idea by proposing that this 5th dimension could be compact, curled up into a circle so small that it escaped detection. If the extra dimension were rolled into itself at a scale smaller than atoms, it would remain invisible to both experiment and everyday experience. The motion of particles through this hidden dimension would appear to us as electric charge. Thus, electromagnetism and gravity could be seen as different aspects of one higher dimensional structure. Although the Kaluza-Klein theory was elegant, it faced challenges. It explained two forces but not the others, and no evidence existed for the tiny circular dimension it required. Still, the concept endured because it revealed something profound. When light and gravity are described together, they demand a geometry richer than the one we perceive. Higher dimensions were not a fantasy, but a mathematical consequence of unification. Decades later, as quantum theory matured, new attempts arose to combine it with relativity. The quantum world is ruled by probabilities, while general relativity describes smooth curvature. Uniting them proved immensely difficult. The equations that govern quantum fields become unstable when gravity is included. Infinities appear that cannot be removed by standard techniques. Yet again, light pointed the way forward. The photon, as the carrier of the electromagnetic force, behaves as a quantum particle and yet fits perfectly within the curved spacetime of relativity. Any future theory of everything would need to reproduce this delicate harmony across all forces. In the 1970s, a new idea began to take shape: string theory. Instead of treating particles as point-like objects, it imagined them as tiny vibrating strings. Each vibration mode corresponded to a different particle. Some modes represented electrons or quarks, while others represented force carriers like photons or gravitons. When physicists wrote the equations governing these strings, they found that consistency required additional dimensions. In most versions, the universe had 10 spatial dimensions and 1 of time. At first, this seemed implausible. How could such extra dimensions exist when we see only 3? But the mathematics was clear. Without them, the theory fell apart. The vibrations of strings could only produce a stable, finite set of results if spacetime contained these hidden dimensions. Like Klein's earlier proposal, these dimensions could be compact, curled up into complex geometric shapes called Calabi-Yau manifolds, their structure influencing the properties of the particles we observe. Light's role within this framework remained essential. The photon emerged naturally as one of the lowest vibration modes of the string, a simple oscillation representing a massless excitation of the electromagnetic field. Its constancy and timelessness were built into the geometry of the higher dimensional space. In a sense, light became a window into these hidden dimensions, not directly visible, but encoded in the mathematics that described its motion. Meanwhile, physicists continued to test the limits of these ideas experimentally. Particle accelerators such as those at CERN searched for evidence of extra dimensions by looking for missing energy in collisions, signs that particles might be slipping into unseen directions. So far, no such evidence has been found, but the experiments have provided constraints that guide theory. If higher dimensions exist, they must be extraordinarily small, perhaps billions of times smaller than a proton. Yet even without direct detection, the higher dimensional perspective has reshaped how scientists think about light and space-time. The equations of modern field theory reveal that the photon is not a unique exception, but part of a family of force carriers, gauge bosons, each corresponding to a different symmetry of nature. These symmetries, when extended into higher dimensions, unify beautifully, suggesting that all forces may arise from a single geometric principle. The constancy of the speed of light becomes, in this view, a manifestation of a deeper invariance, the symmetry of the universe's geometry across all dimensions. Light moves as it does not because it is special, but because the structure of space-time itself allows nothing else. Its speed is the expression of the universe's shape, the way energy and geometry interlock across both visible and hidden dimensions. This concept, though abstract, leads to testable predictions. If extra dimensions influence the geometry of space-time, they could subtly alter the behavior of light at very high energies or in strong gravitational fields. Physicists now design experiments to detect such effects, from precision measurements of atomic transitions to gravitational wave observatories scanning for tiny deviations in the propagation of light-like signals. Each test brings us closer to confirming or ruling out the existence of dimensions beyond our perception. The photon, meanwhile, remains our constant companion in this exploration. It carries within it the clues to both relativity and quantum mechanics. It embodies the boundary between time and timelessness, locality and non-locality, the familiar and the hidden. By studying how it moves, how it interacts, and how it defines the speed of causality, we continue to peel back the layers of the universe's structure. In this pursuit, the role of light becomes philosophical as well as physical. The same entity that makes vision possible also reveals the limits of vision. The same constant that binds our measurements also marks the frontier of our understanding. When physicists look at a photon, they are not merely observing a particle of light, they are glimpsing the framework of existence itself. And so, through the photon's strange relationship with space and time, we are led to an extraordinary conclusion. Light is not just part of the universe's design. It may be the blueprint of that design. It shows us that reality is not static, but dynamic, woven from connections that extend far beyond the dimensions we know. The next step is to explore how this geometry, when curved by gravity, shapes the motion of light itself, and how the bending of that motion reveals the invisible structure of space-time. The relationship between light and gravity is one of the most revealing in all of physics. When Einstein extended his theory of relativity to include acceleration and gravitation, he discovered that light would not simply travel in straight lines through space, but would follow the curvature of space-time itself. In this vision of the universe, gravity was no longer a force acting at a distance, as Newton had imagined. It was the warping of geometry caused by mass and energy. Matter tells space-time how to curve, and space-time tells light how to move. To understand this, imagine a beam of light passing near a massive object, such as a star. In Newton's view, gravity would have no effect on light because light has no mass. But in Einstein's framework, mass bends space-time, and light must follow the curved geometry. The deflection is small but measurable, and in 1919 it was measured for the first time. During a total solar eclipse, Arthur Eddington's expedition observed that the apparent positions of stars near the sun's edge were slightly shifted from their usual places. The amount of this shift matched Einstein's prediction precisely. That observation changed the course of science. For the first time, humanity saw direct evidence that space and time could bend, that light could trace the shape of gravity's invisible geometry. The sun, through its immense mass, had turned the surrounding region of space-time into a lens, focusing starlight like glass bends rays. Newspapers around the world announced that Newton's universe had yielded to Einstein's. Over the following century, this phenomenon, gravitational lensing, became one of the most powerful tools in cosmology. When light from a distant galaxy passes near a massive cluster of galaxies, the cluster's gravity bends and magnifies the light, creating arcs, rings, or multiple images of the same source. These distortions reveal not only the position of visible matter, but also the presence of invisible mass, dark matter. By studying how light curves, scientists can map the unseen scaffolding that holds the cosmos together. In the deepest sense, light does not just respond to gravity, it reveals it. The motion of photons traces the contours of space-time's fabric. Where the geometry curves, light follows. The more strongly space-time bends, the more extreme the deflection becomes. Near a black hole, the curvature grows so intense that light can orbit the object in closed loops. Closer still, at the event horizon, even those orbits become impossible. The escape velocity equals the speed of light, and photons attempting to leave are trapped forever. The black hole represents the ultimate meeting point of light and geometry. Here, the photon's constancy meets gravity's curvature, and the equations of physics approach their limits. In 2019, the Event Horizon Telescope collaboration captured the first direct image of this boundary, a dark shadow surrounded by a glowing ring of light. That light came from photons bent around the black hole's immense gravity, completing multiple orbits before reaching us. It confirmed in exquisite detail that light follows the geodesics of curved spacetime, exactly as general relativity predicts. Yet even in these extreme environments, light maintains its speed. It slows in appearance when viewed from afar, but this slowing is not physical. It arises from the stretching of time near massive objects. The photon itself continues along its path at the universal constant, untouched by time or rest. What changes is the geometry through which it moves. To an outside observer, light near a black hole seems to crawl, redshifted and weakened, as if time itself were dilating. From light's perspective, though, there is no passage of time at all. This interplay of constancy and curvature reveals something profound. The geometry of spacetime is not a static background, but a dynamic entity shaped by energy and radiation. Even light, though massless, contributes to this curvature through its energy and momentum. Streams of photons can bend spacetime minutely, and in the early universe, the radiation density was high enough for this effect to matter. In that primordial epoch, light not only traveled through space-time, it helped shape its expansion. As technology advanced, scientists learned to measure the bending of light with extraordinary precision. The Hubble Space Telescope, and more recently, the James Webb Space Telescope, have captured images of galaxies distorted into elegant arcs and mirrored shapes, stretched by gravitational lenses billions of light-years away. These natural lenses act as cosmic magnifiers, allowing astronomers to see objects too distant or faint to observe directly. Every curve of light, every distortion in the image, encodes the geometry of invisible matter and energy. Even the faintest glow in the universe, the cosmic microwave background, bears the imprint of light's long journey through curved spacetime. As photons from the Big Bang traveled across the expanding universe, their paths were deflected by clusters and filaments of dark matter, leaving subtle patterns in the sky that scientists can now map with precision. These maps confirm that the same geometry governing light on small scales also shapes the cosmos on the largest scales. Through light, we have learned that gravity is not a mysterious pull, but a manifestation of geometry, and that geometry itself is dynamic, alive, and responsive to energy. When we speak of light bending, we are really observing the universe expressing its structure. The photon's constant speed defines how spacetime behaves, and spacetime, in turn, defines how the photon moves. The two are inseparable, two aspects of one grand continuum. This understanding leads naturally to another question. If light and gravity are both expressions of geometry, could they be unified as parts of a single, higher dimensional reality? The idea that additional dimensions might reconcile these forces is not an invention of modern speculation, but a direction demanded by the mathematics of unification itself. The same logic that links mass and energy, space and time, may link the visible universe to hidden dimensions beyond our perception. The search for those dimensions, for the deeper geometry that joins light and gravity, is one of the most profound quests in science. It challenges not only our understanding of physics, but our conception of reality. And at the center of that search, as always, stands the photon, timeless, massless, and constant, showing us that to follow light is to trace the very architecture of the universe. For centuries, scientists dreamed of finding one simple principle that could describe every force in nature. They sought a single thread running through the cosmos, a law from which all others could be derived. That dream has guided generations of physicists, from Newton's unification of celestial and terrestrial motion, to Maxwell's merging of electricity and magnetism, and finally to Einstein's revelation that space and time form a single continuum. Each breakthrough revealed a deeper order, and each left one mystery unsolved. Einstein himself spent the last decades of his life searching for the next step, a theory that would unite gravity, the force that shapes the geometry of space-time, with electromagnetism, the force that governs light. He believed these two could not be separate. Both influence the motion of energy, and both propagate at the same constant speed of light. The challenge was to express them in a single mathematical language. The first clue to such unification came in the 1920s through the work of Theodore Kaluza, a mathematician who extended Einstein's equations of general relativity by adding a fifth dimension to space-time. In his model, the universe had not 4, but 5 coordinates, 3 of space, 1 of time, and 1 additional spatial direction unseen by human senses. When Kaluza substituted this expanded geometry into Einstein's field equations, something remarkable happened. The equations describing gravity naturally split into 2 parts. One set represented the familiar curvature of space-time, while the other exactly reproduced Maxwell's equations for electromagnetism. Kaluza had discovered that by simply adding one more dimension, gravity and light emerged as different aspects of the same geometry. What had once seemed like 2 independent forces became unified within a higher dimensional framework. The electromagnetic field arose from the way space-time curved within this hidden 5th direction. A few years later, the Swedish physicist Oskar Klein refined the idea further. He proposed that this extra dimension might be compact, curled up into a tiny circle so small that we could never perceive it directly. Just as a hose seen from far away looks one-dimensional, but up close reveals a circular cross-section, the universe might possess small, wrapped dimensions at every point in space. Particles moving through this curled dimension would appear to us as possessing electric charge. Thus, charge and electromagnetism were not separate entities but the shadow of motion in a hidden direction. This vision was stunningly elegant. It suggested that the world we see is a projection of a richer geometry. Gravity, electromagnetism, and the motion of light all arise from how that geometry folds and curves. The photon, in this picture, is not a separate particle, but a ripple of the 5-dimensional fabric itself. Its constancy and timelessness reflect the symmetry of that higher dimensional space. The Kaluza-Klein theory captivated many physicists, but it was ahead of its time. The technology to test its predictions did not exist, and the discovery of the strong and weak nuclear forces in the mid-20th century complicated the picture. 2 forces were no longer enough to explain the universe's interactions. The dream of unification grew larger and more intricate. Still, the idea that extra dimensions could unify forces never disappeared. When quantum mechanics rose to prominence, physicists found that particles could be described as excitations of underlying fields. These fields, like the electromagnetic field, filled all of space and carried the symmetries of nature. The concept of gauge symmetry, the mathematical invariance underlying these forces, became the new language of physics, and it was light once again, that revealed the pattern. The photon is the carrier of the electromagnetic force, a particle born from a symmetry labeled U1 in the language of group theory. The weak force has its own carriers, the W and Z bosons, associated with a larger symmetry, SU2. The strong nuclear force, which binds quarks together inside atomic nuclei, is governed by an even richer symmetry, SU3. These patterns suggested a hierarchy, as though the forces were branches of a single tree with shared roots. In the 1970s, physicists began constructing grand unified theories that combine these three quantum forces into a single mathematical framework. In many of these theories, the different forces are manifestations of one underlying interaction that becomes apparent only at extremely high energies, energies present in the early universe, but unreachable in ordinary laboratories. In these models, the photon, gluons, and weak bosons are all different vibrations of a unified field. As the universe cooled, the symmetries broke apart and the forces differentiated, much as water freezes into ice and develops structure from uniformity. Gravity, however, remained outside this unification. It resisted incorporation into the quantum world. When physicists tried to quantize Einstein's curved spacetime, to treat gravity like the other forces, the mathematics produced infinities that no method could cancel. The very fabric of space refused to be chopped into quantum pieces. Yet light continued to hint at the path forward. Its constant speed, its masslessness, and its role in defining space-time geometry all suggested that gravity and light were two expressions of one principle not yet fully understood. By the late 20th century, that principle began to take form in a new framework: string theory. Instead of point-like particles, the fundamental building blocks of the universe were envisioned as tiny vibrating strings. Each vibration pattern corresponded to a different particle. One mode produced the graviton, the quantum of gravity. Another gave rise to the photon. The equations of string theory required extra spatial dimensions, not one, but 6 or 7 beyond the familiar 3, to remain consistent. In this higher dimensional picture, the universe we perceive is like a three-dimensional surface, or brane, floating in a larger multi-dimensional space. Light and other forces might be confined to our brain, while gravity, through the graviton, could spread into the additional dimensions. This could explain why gravity appears so much weaker than the other forces. Its influence is diluted through the extra spatial directions. Such models are not speculation born of imagination, but necessities of mathematics. The equations demand them to preserve consistency and avoid paradox. Each dimension adds new degrees of freedom that allow the unification of quantum mechanics and relativity to proceed without contradiction. And through all of this, the photon remains the guide, the entity that threads seamlessly between the quantum and the geometric, the wave and the particle, the seen and the unseen. The implications of these ideas stretch far beyond abstract theory. If extra dimensions exist, they could leave subtle fingerprints in experiments. High-energy collisions in particle accelerators might occasionally produce energy that seems to vanish, escaping into hidden directions. Gravity might deviate slightly from its predicted strength at extremely small distances, if it can leak into higher dimensions. Detecting such effects would provide direct evidence for the geometry that Kaluza and Klein first imagined a century ago. Even without direct proof, the pursuit of unification has already changed how we view the cosmos. It has revealed that the same constant that governs the motion of light also anchors the structure of space-time. The universe may be far richer than the three-dimensional arena we inhabit, a tapestry woven from dimensions compacted beyond perception. And through this tapestry, light remains the messenger, carrying not just information about the visible universe, but clues about the unseen geometry that underlies it. The search for unity continues. Physicists now explore new versions of these theories, such as M-theory, which unites all string frameworks into a single 11-dimensional model. In these formulations, light, gravity, and matter are not separate entities, but different manifestations of one underlying vibration of space itself. Whether these dimensions will ever be directly detected remains unknown, but their mathematical elegance suggests that the universe's deepest simplicity may lie in this higher dimensional harmony. Light, once thought to be just illumination, may in fact be the key to revealing the full structure of existence. Its constancy, its ability to bridge quantum theory and relativity, and its role in shaping the geometry of spacetime all point to the same conclusion. The universe is a unified whole, and light is the thread that weaves it together. The idea that all of nature's forces could emerge from a single underlying framework is not only beautiful but deeply practical. The more precisely scientists have studied light, electromagnetism, and gravity, the more they have seen the same mathematical structures repeat across vastly different scales. Whether describing the orbit of a planet or the oscillation of an electron, the equations share a geometric language. This repetition suggests that reality is built upon symmetry, patterns that remain unchanged even as the forms they govern appear different. In the early decades of the 20th century, symmetries began to reveal themselves as the true backbone of physical law. Each force of nature corresponds to a kind of symmetry, a rule stating that the laws of physics remain unchanged under certain transformations. For electromagnetism, that symmetry is the ability to change the phase of the electromagnetic field, to rotate its internal direction without altering measurable quantities. The photon exists because of this invariance. It is the quantum messenger that ensures the symmetry is respected in every interaction. When these ideas were extended to include other forces, new symmetries emerged. The weak force, responsible for radioactive decay, obeys a similar but more complex rule, while the strong force that binds quarks inside protons and neutrons follows an even richer symmetry. Each of these forces has its own corresponding particles, W and Z bosons for the weak interaction, gluons for the strong. What unified field theories propose is that these different symmetries are actually parts of a larger, more encompassing pattern, one that was fully symmetrical in the earliest moments after the Big Bang. At extremely high energies, the universe may have possessed a single unified force. As it expanded and cooled, that symmetry broke, splitting into the separate forces we now observe. This is analogous to the way water freezes into ice. Above 0 degrees Celsius, the molecules move freely in a uniform liquid. Below that temperature, they lock into a rigid lattice, breaking the symmetry of the liquid state. Likewise, as the early universe cooled, its original symmetry fractured, creating distinct interactions that now govern matter. Light plays a central role in this story because it remains the most perfect expression of symmetry we know. The photon has no mass, no electric charge, and no intrinsic direction. It is pure energy, unburdened by the properties that distinguish other particles. This neutrality allows it to mediate electromagnetic interactions across infinite distances, maintaining the balance that Maxwell's equations demand. It is the simplest and yet most fundamental carrier of information in the universe, the direct imprint of symmetry itself. When theorists began to explore how these symmetries might fit together in higher dimensions, a pattern emerged. The equations governing electromagnetism, the weak force, and the strong force could all be derived from a single higher dimensional framework. In these models, the forces we perceive as distinct are projections of a unified geometry, much like shadows of one object cast on different walls. The photon, gluon, and weak bosons are not separate species, but different vibration modes of the same fundamental field. The mathematics behind these theories is demanding, but its message is simple. Nature's complexity may arise from simplicity hidden in extra dimensions. If the geometry of space extends beyond what we can perceive, then the properties of particles, their masses, charges, and interactions may reflect how those hidden dimensions are folded or compacted. In this view, the diversity of matter is the echo of geometry beyond our senses. Such reasoning led directly to modern string theory, where particles are not points, but tiny one-dimensional strings vibrating at specific frequencies. Each vibration corresponds to a different particle, and the way those strings move through higher dimensional space determines the physical constants we measure. The photon in this framework is the simplest vibration, a harmonic of pure energy that requires no rest mass. Gravity, represented by another vibration called the graviton, appears naturally alongside it. In this way, light and gravity are not separate forces to be joined artificially, but siblings born from the same underlying structure. One of the most intriguing consequences of these models is the possibility that gravity may extend into extra dimensions, while light remains confined to the three we perceive. This could explain why gravity is so much weaker than the other forces. Its lines of influence are diluted through the hidden spatial directions, spreading thinly across the larger geometry. Some physicists call this the brane world scenario, our visible universe as a three-dimensional surface embedded in a higher dimensional cosmos. In this picture, photons, electrons, and all ordinary matter are trapped on the brane, while gravity, through its quantum carrier, leaks into the higher space. If such extra dimensions exist, they are not simply abstract mathematics. They might leave measurable traces in high-energy physics or cosmology. At the Large Hadron Collider, scientists look for missing energy in particle collisions, a sign that invisible particles may have slipped into hidden dimensions. Precision experiments measuring the force of gravity at sub-millimeter scales test whether it deviates from Newton's law at very short distances. Thus far, no deviations have been found, but each experiment tightens the limits and refines the theory. Beyond the laboratory, astronomers search the cosmos for clues. If extra dimensions alter how gravity behaves, they might influence how galaxies form or how gravitational waves propagate through space. Detectors like LIGO and Virgo already observe these waves, ripples in space-time caused by merging black holes and neutron stars. Subtle differences in their behavior could one day reveal the influence of hidden dimensions. Through all these efforts, light remains both the measuring stick and the messenger. We use it to time the arrival of gravitational waves, to track the expansion of the universe, and to calibrate the fundamental constants of nature. Even when exploring dimensions we cannot see, photons carry the data that allows us to infer their existence. Light defines what is observable. It is the medium through which the invisible becomes known. The pursuit of unification is not yet complete, but each step brings us closer to understanding why the universe has the form it does. Light and gravity, so different in strength and behavior, may be two expressions of one deeper order, revealed only when we consider that the cosmos may extend beyond the familiar three dimensions. Whether these higher dimensions are vast or curled into infinitesimal scales, their fingerprints may be etched into the way light moves, bends, and interacts with matter. In the end, light's constancy continues to guide us. Its unwavering speed, its masslessness, and its perfect symmetry are not accidents. They are the keys to a geometry that may stretch beyond the limits of perception. To follow light is to follow the path toward unity, the path that connects the tangible to the hidden, the visible to the invisible, the finite to the infinite. At the deepest level, the unification of forces reveals a remarkable truth. Geometry itself might be the origin of everything. The shapes and symmetries of space are not passive arenas in which matter acts, but the very source of the particles and fields that fill the universe. Every photon, every electron, every quantum of energy could be understood as a vibration of geometry, a resonance within the multidimensional fabric of existence. In this view, the photon becomes more than just a messenger of light. It becomes the simplest possible excitation of the underlying space-time field. Its properties, massless, chargeless, and traveling at the universal constant speed, arise not from arbitrary rules, but from the symmetry of the cosmos itself. When that symmetry is perfect, the photon remains massless. If the symmetry breaks, particles gain mass. This is not philosophical poetry, but the central idea behind the modern standard model of particle physics. The Higgs field, for example, imparts mass to particles by breaking the symmetry that otherwise would make them behave like light. The same principle may extend to gravity. In higher dimensional theories, such as string theory and its successor, M theory, space-time itself becomes a dynamic entity composed of multidimensional objects, strings, membranes, and beyond. Light and gravity in this context are two kinds of vibrations within that extended geometry. The photon arises from oscillations confined to our three-dimensional world, while the graviton, the hypothetical quantum of gravity, represents oscillations that ripple through all dimensions. In this sense, the two forces are united not by force lines or particles, but by geometry's deeper harmonies. The idea that all forces are manifestations of geometry brings physics full circle. In the 17th century, Isaac Newton described gravity as an invisible attraction acting across space. In the 19th, Maxwell showed that electric and magnetic fields are aspects of a single electromagnetic geometry. Einstein revealed that gravity itself is geometry, the curvature of space-time. Kaluza and Klein then demonstrated that when one adds more dimensions to that geometry, electromagnetism appears naturally. Each step has drawn the same conclusion. To understand the universe, we must understand the shape of space. But how can we test a shape that hides beyond perception? Physicists have turned to both the smallest and the largest scales for answers. On the smallest scales, particle accelerators probe the quantum fields that may carry signatures of hidden dimensions. On the largest, telescopes map the cosmic microwave background, the relic radiation from the Big Bang, searching for subtle patterns that could hint at the influence of extra-spatial directions in the universe's earliest moments. Some of the most exciting tests involve gravity itself. If extra dimensions exist, their geometry could slightly alter the inverse square law of gravitational attraction at extremely short distances. Experiments using exquisitely sensitive torsion balances have measured gravitational forces between small masses separated by less than a millimeter. So far, Newton's law holds perfectly, but each new generation of measurements pushes deeper, narrowing the possible scale of hidden dimensions. In the realm of high-energy physics, scientists at the Large Hadron Collider and other accelerators continue to search for deviations from the standard model that might signal the presence of new geometry. When two protons collide at near-light speeds, they create a burst of energy dense enough to momentarily probe the fabric of space-time itself. If energy or momentum seems to vanish from the collision, it could mean that some particles have slipped into hidden dimensions. Such missing energy signatures would be one of the clearest indicators that the universe extends beyond our visible three. Yet even without direct detection, the mathematics of unification remains compelling. The consistency of these higher dimensional theories, their ability to resolve the contradictions between quantum mechanics and general relativity, and their natural inclusion of the photon and graviton within one framework all point to their potential truth. These models do not merely describe the universe, they explain why it must have the properties we observe. The role of light within these theories remains central. The photon's behavior reflects the geometry of space-time with exquisite precision. It is both the probe and the proof. Every experiment that measures its constancy, every observation that detects its bending by gravity, every calculation that traces its quantum interactions reinforces the notion that light is the most direct expression of space-time's structure. To imagine the universe in higher dimensions is not to drift into speculation, but to follow the mathematics wherever it leads. Just as earlier generations once believed space to be flat until evidence proved it curved, so too might we one day find that our four-dimensional view is only a shadow of a far richer geometry. The clues lie all around us, written in the paths of photons that traverse the cosmos. When we look at the night sky, we are seeing not just the distant past, but the structure of the universe itself illuminated by light's journey. The patterns of galaxies, the bending of their light, the spectrum of their radiation, all are governed by the interplay between geometry and the speed of light. Every photon is a messenger from that deeper reality, carrying the information of both what exists and how existence is shaped. Perhaps the most remarkable aspect of all this is how naturally it fits into the principle of unity that has guided science from the beginning. The same constant, the speed of light, that defines motion in relativity also determines the scale of quantum phenomena, links energy to mass, and sets the boundary of causality. It is the ratio that binds the vast and the minute, the slow and the instantaneous. In a very real sense, light is the common currency of the cosmos. The pursuit of unification continues because the evidence compels it. Every experiment confirming relativity, every discovery in quantum physics, and every observation in cosmology reinforces the idea that the universe is a single, coherent system. If higher dimensions exist, they will not remain hidden forever. The tools of science, telescopes, accelerators, and the ceaseless precision of light itself will eventually reveal their presence. Until then, light continues to be our most faithful guide. It is the constant that will not bend, the messenger that never tires, the key that has unlocked every door we have opened in our search for truth. Through its constancy and its geometry, it reminds us that reality is not fragmented but whole, not chaotic but unified. The next step in our journey follows the same thread, how the geometry that light reveals, the bending of space, the warping of time, transforms our understanding of gravity itself. For it is through light's path that we first glimpse space-time's curvature, and it is through that curvature that the next layer of the universe's design begins to unfold. To understand gravity is to understand how light moves. For centuries, gravity was seen as a mysterious pull, an invisible force reaching across empty space. Newton's equations described it perfectly for the motions of planets and falling apples, yet they did not explain what gravity is. Why should two objects separated by vast emptiness attract each other? What transmits that influence? The answer, it turned out, was not a force at all, but the shape of space itself. Einstein's general theory of relativity replaced Newton's gravitational pull with geometry. According to this vision, matter and energy curve the fabric of space-time, and that curvature dictates how objects, and light, move. Planets orbit stars not because they are tugged by an invisible string, but because they follow the straightest possible paths through a curved geometry. Those straight paths are called geodesics, and light, with its constant speed, always travels along them. If space were completely flat, light would move in perfectly straight lines. But space is not flat. The presence of mass and energy bends it, creating dips and warps like the surface of a stretched fabric under a heavy weight. A photon moving near a massive object like the Sun must follow this curve. From our point of view, its path bends, but in the geometry of space-time, it is still traveling straight through a curved world. This prediction was tested dramatically in 1919, when astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the brief moments when the sun's light was blocked by the moon, the team photographed the stars near its edge. According to Einstein's theory, the sun's gravity should slightly deflect their light, shifting their apparent positions. When the plates were developed, the measurements matched Einstein's calculations exactly. The news traveled around the world. The curvature of space was no longer theory. It had been seen in the bending of light. That moment changed not just physics, but the human view of reality. The universe was no longer a stage upon which events occurred. It was an active participant in every process. The fabric of space and time could stretch, twist, and curve, shaping the flow of energy and matter within it. Light, the fastest and most fundamental traveler in the cosmos, became the probe by which this geometry could be revealed. As instruments improved, evidence for space-time curvature multiplied. Light from distant galaxies bends as it passes through clusters of other galaxies, producing arcs and rings of distorted images, a phenomenon now known as gravitational lensing. These cosmic lenses can magnify objects billions of light-years away, acting like natural telescopes built by gravity itself. Through them, astronomers can study the early universe, observe galaxies too faint to see otherwise, and even map the distribution of dark matter, the unseen mass that shapes the large-scale structure of the cosmos. The same principle explains one of the universe's most extreme environments, the black hole. When an enormous amount of mass collapses into a small region, the curvature of space-time becomes so steep that not even light can climb out. The boundary of this region is called the event horizon, the point beyond which all paths lead inward. It marks the place where geometry itself closes off from the rest of the universe. For anything crossing that horizon, space and time trade roles. Moving forward in time means moving deeper toward the center. Yet even at this frontier, light continues to reveal the hidden geometry. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow in the galaxy Messier 87. The bright ring seen in that image was light orbiting the black hole, its path bent almost into a circle by the immense curvature. The darkness at the center was not an object, but a region from which no light can escape. That photograph, a ring of photons tracing the shape of space-time, stands as one of humanity's greatest scientific achievements, proof that Einstein's geometry holds even at the edge of the possible. Light also shows how gravity stretches time. In strong gravitational fields, clocks tick more slowly relative to those in weaker fields. This gravitational time dilation means that light climbing out of a gravitational well loses energy, its wavelength stretching toward the red, an effect called gravitational redshift. It was first measured on Earth in the 1960s when scientists compared the frequencies of atomic clocks placed at different heights. The clock on the lower floor, deeper in Earth's gravity, ran slightly slower. Today, satellites in orbit must account for both gravitational and motion-induced time dilation for systems like GPS to function accurately. At cosmic scales, the same effect shapes how we observe the universe's expansion. As space stretches, light traveling through it is redshifted, its wavelength lengthened by the growth of the cosmos. Distant galaxies appear redder because their light has traveled through expanding space-time. By measuring these redshifts, astronomers can determine how fast the universe is expanding and how that expansion has changed over time. The very geometry of the cosmos, from the smallest curvature around a star to the vast curvature of the entire universe, is known to us because of light. The unification of light and gravity through geometry also leads to new insights into energy. In Einstein's equations, the same tensor that describes space-time curvature also contains the energy and momentum of matter and radiation. Light contributes to gravity not through mass, but through its energy. A beam of intense radiation can, in theory, curve space-time ever so slightly. In the early universe, when radiation filled all of space, this effect was significant. Light itself helped determine how the cosmos expanded. At the intersection of quantum mechanics and relativity, even more mysteries appear. Near a black hole's event horizon, quantum effects become important. Stephen Hawking showed that pairs of virtual particles constantly form and annihilate in the vacuum. When one member of a pair falls into the black hole while the other escapes, the escaping particle becomes real, carrying energy away as Hawking radiation. This process slowly evaporates black holes over unimaginable timescales, proving that even the most extreme curvature cannot hide forever from quantum light. Through these discoveries, light remains our most faithful instrument for exploring the invisible geometry of reality. It reveals that gravity is not a separate force, but a manifestation of curvature, and that curvature, in turn, shapes everything we see. Every observation, from the bending of starlight to the timing of pulsars, confirms the same truth. Light moves not through space, but through space-time, following the pathways carved by energy and mass. And yet, even this elegant picture is incomplete. When we examine the universe at the smallest scales, where quantum uncertainty rules, the smooth fabric of space-time begins to break apart. Light itself, both wave and particle, seems to dance between the continuous and the discrete. To understand this duality, and how light behaves in a world of probabilities rather than certainties, we must step into the quantum realm, where the next revolution in understanding awaits. As scientists venture deeper into the study of light and gravity, they realize that the smooth geometry of space-time could not be the whole story. On cosmic scales, Einstein's equations describe the bending of light and the warping of time with extraordinary accuracy. Yet at the smallest scales, inside atoms, near singularities, or in the first fractions of a second after the Big Bang, the rules of quantum mechanics dominate. Here, certainty gives way to probability, and the deterministic curves of spacetime blur into a realm of fluctuations. Light, which unites both worlds, becomes the key to understanding where they meet. In the classical view, light travels along geodesics, tracing elegant paths through curved spacetime. But quantum theory tells a different story. A photon does not follow one path. It explores every possible route between 2 points simultaneously. Only when it interacts with matter, or when it is measured, does it appear to have chosen one. Between emission and absorption, its existence is described by a wave function, a mathematical entity encoding probabilities rather than definite positions. Richard Feynman's path integral formulation captures this beautifully. According to his principle, the probability of a photon arriving at a particular point is determined by summing over all the possible trajectories it could have taken, each path contributing with a phase related to the photon's energy and action. The paths that differ greatly from the classical straight line mostly cancel each other out through destructive interference, leaving only those close to the geodesic, the path predicted by relativity, as the dominant ones. In this way, the classical motion of light emerges as an average over countless quantum possibilities. This interplay between quantum uncertainty and geometric determinism lies at the heart of modern physics. It shows that relativity and quantum mechanics are not rivals, but complementary perspectives on the same phenomenon. The geometry of spacetime determines the overall structure of light's motion, while quantum mechanics governs the fine details of how individual photons behave. Together, they describe a universe where geometry is statistical and certainty is an approximation. In laboratories on Earth, these effects can be observed directly. When a single photon passes through a double slit, its probability wave spreads out and interferes with itself, producing a pattern of alternating bright and dark fringes. Each photon lands in a specific spot, but after many photons, the interference pattern emerges, reflecting the underlying wave behavior. If we try to measure which slit the photon passes through, the interference disappears. The act of observation changes the outcome. The experiment demonstrates that light embodies both wave and particle nature simultaneously, depending on how it is measured. This duality becomes even more fascinating when we introduce gravity. According to general relativity, photons always move at the speed of light and follow curved paths in space-time. According to quantum mechanics, they exist in superpositions of paths until an interaction fixes their position. When the two theories are combined, the geometry through which the photon moves is no longer perfectly smooth, but subject to tiny quantum fluctuations. These fluctuations, sometimes called quantum foam, represent the restless, probabilistic nature of space-time itself at the Planck scale, where distances are so small that even the concept of a continuous surface loses meaning. Scientists have not yet fully reconciled these two descriptions, but light offers a path forward. Experiments with highly sensitive interferometers, like those used to detect gravitational waves, already measure distortions in space-time smaller than a proton. Future instruments may one day detect the faint tremors of quantum geometry itself. If the quantum foam of space-time affects the travel of photons, even minutely, it could leave an observable signature, a tiny deviation in the arrival times or polarization of light from distant cosmic sources. On astronomical scales, the curvature of space-time also acts like a natural experiment in quantum optics. When light passes near massive objects, it can take multiple paths around them, producing interference patterns on cosmic scales. These gravitational lensing effects have been observed across the sky, forming arcs and rings that encode both the geometry of space and the quantum coherence of light. Each photon detected from these events has traveled for billions of years, experiencing gravity's curvature and quantum probability together. The merging of quantum mechanics and relativity also reshapes how we think about time. In quantum theory, time appears as a parameter, an external clock against which events are measured. In relativity, time is part of the geometry, intertwined with space and influenced by gravity. To unite these views, physicists must find a description of light that includes both the probabilistic nature of quantum events and the dynamical geometry of space-time. Many believe the key lies in quantizing gravity itself, describing the geometry of the universe in terms of discrete units, much like photons, represent discrete quanta of light. Several attempts to achieve this unification already exist. Loop quantum gravity, for example, proposes that space is composed of tiny loops of quantized geometry woven together like a fabric. In this picture, light travels not through a smooth continuum, but through a network of finite threads, each representing a unit of area or volume. String theory offers another approach, replacing particles with vibrating strings whose interactions naturally include both photons and gravitons, the hypothetical quanta of gravity. In both views, light remains central, the simplest vibration, the cleanest probe of geometry, the constant that ties all forces together. Even at the boundaries of black holes, where curvature and quantum effects converge most violently, light continues to guide our understanding. Photons skimming just outside the event horizon can orbit the black hole in unstable rings, tracing the point where gravity and geometry balance perfectly. Quantum effects near this region generate Hawking radiation, in which pairs of particles and antiparticles emerge from the vacuum. One falls into the black hole, while the other escapes, carrying energy away. This faint radiation, though still undetectable from distant astrophysical black holes, represents one of the most important insights into how light and gravity interact at the quantum level. Through all these explorations, one truth remains constant. Light reveals the structure of the universe, no matter how deep we look. From the smooth curvature of space-time to the restless quantum fluctuations at its foundations, the photon acts as both participant and observer, both messenger and measure. The bending of light shows us gravity's shape. The interference of light shows us quantum probability. Together, they form a picture of reality that is at once elegant and unfinished. As our instruments and theories grow more precise, we stand closer than ever to answering the greatest question of all. Can light, through its geometry, its quantum nature, and its constancy, lead us to a complete description of the universe? The search continues, but the direction is clear. Every beam, every photon, every ripple of light is a piece of that answer waiting to be read. The deeper physicists explored the relationship between light and gravity, the more they saw that each acted as a mirror for the other. Gravity bends light, and light reveals gravity's shape. Both are geometric phenomena written in the same mathematical language. One curves space-time, and the other traces that curvature perfectly. This unity between motion and geometry reaches its most profound form near the extremes of the universe, where light encounters the limits of space-time itself. To describe this interplay, Einstein's field equations link the distribution of matter and energy to the curvature of space-time. On one side of the equation lies geometry, how distances, angles, and time intervals behave. On the other lies energy, the density of matter, radiation, and pressure within that region. Light contributes to both sides at once. It moves along the geodesics carved by energy, yet its own energy adds to the curvature. Even a beam of photons has weight in the sense that it warps space-time minutely as it passes. The cosmos is therefore self-shaping. Light defines geometry, and geometry defines light's path. In the early universe, this relationship determined the first great structure of everything. Just after the Big Bang, radiation dominated all existence. The density of photons and other relativistic particles was so immense that their combined energy governed the expansion rate of space-time. The universe's early growth was driven by light itself, not the light of stars, which had not yet formed, but a sea of high-energy photons filling every direction. When the universe cooled enough for atoms to form, light was free to travel unimpeded, leaving behind the faint cosmic microwave background we still detect today. Its uniformity and tiny ripples tell us exactly how the geometry of space evolved from those first moments. The bending of light also allows us to map this evolution in the present. Massive galaxy clusters act as lenses that magnify distant galaxies behind them. The degree of distortion reveals how much mass, visible and invisible, resides in the lensing cluster. By measuring these distortions across many regions of the sky, astronomers can reconstruct the three-dimensional distribution of dark matter. Even though dark matter emits no light, its gravitational fingerprint is written in the way it bends the photons passing nearby. In this way, light paints the shape of the unseen. Perhaps nowhere is the connection between light and curvature more dramatic than at the edge of a black hole. Here, space-time becomes so warped that light can orbit the object in perfect circles, forming what physicists call the photon sphere. A single photon could, in theory, circle a black hole endlessly, trapped on the knife edge between escape and capture. Slightly closer, every path leads inward. Slightly farther, photons spiral away. The photon sphere marks the boundary where geometry and light balance in perfect tension. This balance also defines the event horizon, the ultimate point of no return. At this boundary, space-time curves back upon itself so steeply that all future paths lead toward the center. The equations describing this region predict that time, for an outside observer, slows to a halt. A photon emitted near the horizon appears to lose energy endlessly, its wavelength stretching into infinite redshift. From the outside, it seems frozen at the edge, never quite escaping. From the photon's own perspective, there is no delay. Its emission and absorption remain a single event. To study these extremes, scientists now combine observations from every part of the electromagnetic spectrum: radio, infrared, visible, ultraviolet, X-ray, and gamma-ray light, to form a complete picture of how gravity shapes radiation. The Event Horizon Telescope uses radio waves. The Chandra X-ray Observatory captures the hot plasma swirling around black holes, and optical telescopes track the stars that orbit them. Together they provide a unified portrait of curved space-time in action. Gravitational waves, first detected in 2015, offer yet another dimension to this story. They are ripples in space-time itself, generated by accelerating masses like merging black holes or neutron stars. These waves travel at the speed of light, confirming that both light and gravity share the same causal limit. In fact, Einstein's equations predict that gravitational waves must propagate exactly at light speed, a prediction confirmed by observations of a neutron star collision, whose light and gravitational signals reached Earth almost simultaneously after traveling for over 100 million years. This equality between light and gravitational waves is more than coincidence. It means that the curvature of space-time and the electromagnetic field are governed by the same fundamental geometry. Both transmit information about the universe without requiring a medium, and both define the boundaries of causality. The universe itself, viewed through this lens, behaves like a vast resonant system where geometry vibrates in different modes. One we call light, another we call gravity. Einstein's theory continues to withstand every test. Precision measurements of light deflection by the sun, time dilation near massive bodies, and the gravitational redshift of light emitted by stars all agree with his predictions to many decimal places. Space-based observatories like Gaia and JWST refine these measurements further, confirming that the geometry of the cosmos behaves exactly as light's motion dictates. Even the orbits of stars around the supermassive black hole at the center of the Milky Way reveal the same interplay of curvature and constancy. Yet at the same time, quantum mechanics whispers that there is more to uncover. In regions where space-time curvature becomes extreme, inside black holes or at the birth of the universe, Einstein's smooth geometry cannot hold. The very concept of a continuous fabric breaks down, replaced by quantum uncertainty. Here again, light is our only guide. Whether it takes the form of photons, Hawking radiation, or the echoes of gravitational waves, it carries the imprint of physics beyond relativity's reach. The challenge of modern physics is to merge these two realms, the smooth geometric world of Einstein and the probabilistic quantum world revealed by light itself. The solution will not discard either theory, but unite them, perhaps through a deeper understanding of space-time as a quantized, multi-dimensional structure. Light, as the boundary between these worlds, is the key that will unlock that union. In the end, every insight into gravity has come through light, the way it bends, delays, redshifts, or disappears. We see curvature through photons, we measure time through their oscillations, and we know the universe's shape by the way they scatter across the sky. Light is the perfect storyteller of geometry because it cannot be fooled. It moves always at the same speed, tracing the universe's truth line by line, photon by photon. And so, having followed light through the curved pathways of gravity, we now descend deeper, into the realm where light's own nature becomes uncertain, divided between wave and particle. The next step takes us to the very heart of quantum reality, where the behavior of light challenges our most basic understanding of what real means. Light is the universe's greatest paradox. It is a wave that ripples through space, spreading smoothly and continuously. Yet, it is also a particle, a single quantum of energy that arrives in discrete packets. This duality, revealed by experiments and confirmed by quantum mechanics, reshaped our understanding of reality itself. It showed that the universe is not built from solid objects, but from probabilities, vibrations, and the limits of what can be known. The story began in the early 20th century when scientists realized that classical physics could not explain the behavior of light. Max Planck's solution to the problem of blackbody radiation introduced the idea that energy comes in quantized units. A few years later, Albert Einstein took the leap that changed everything. He proposed that light itself consists of these quanta, photons. This simple but revolutionary idea explained the photoelectric effect, where light ejects electrons from metal surfaces only if its frequency is above a certain threshold. Light's energy, Einstein realized, depends on its color, not its brightness. Yet, at the same time, experiments such as the double-slit test revealed light's unmistakable wave nature. When photons pass through two narrow openings, they create an interference pattern, alternating bands of brightness and darkness, even when sent one photon at a time. This means that each photon behaves like a wave, exploring all possible paths simultaneously, and interferes with itself before being detected as a single particle. Only upon measurement does it choose a definite outcome. This is the essence of quantum mechanics. Reality exists not as a set of determined events, but as a spectrum of possibilities, until observation collapses them into a single history. The photon embodies this mystery perfectly. It can act as a particle or a wave, depending on how it is observed. Both descriptions are correct, but neither alone is complete. Quantum electrodynamics, QED, provides the mathematical framework that unites these behaviors. Developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, it describes how light interacts with charged particles through the exchange of photons, both real and virtual. It is the most precise theory ever created, with predictions matching experiments to an accuracy of 1 part in a trillion. In QED, the electromagnetic field fills all of space, and photons are its quantized ripples. Even the vacuum is alive with fluctuations, where pairs of virtual particles appear and vanish too quickly to be seen. Light's duality extends beyond theory into the foundation of modern technology. Lasers, solar cells, and quantum computers all rely on controlling photons at the quantum level. Each of these inventions uses light's coherence, the synchronization of its waves, to create stability from uncertainty. Through them, we have learned not just to understand light, but to use its quantum nature to shape information and energy themselves. And beneath it all lies a deeper truth. Light reveals that the universe is not deterministic, but relational. Everything that exists does so through interaction. A photon has meaning only when emitted or absorbed, only when part of an exchange. It connects one event to another, stitching space-time together through the transfer of energy. Light, in this sense, is not merely something that travels through reality. It is what makes reality communicable. The photon's duality is not a contradiction, but a reflection of nature's completeness. What seems paradoxical to us is harmony at a deeper level. A reminder that the universe's most fundamental truths are not singular, but dual, united in symmetry. Through light, we glimpse the quantum order beneath the visible world, a realm where probability is law and where every particle is also a wave. The speed of light is not merely a measurement, it is the cosmic speed limit that defines the structure of reality. It determines what can influence what, sets the rhythm of time, and establishes the very notion of causality. Without it, the universe would lose its order. Every event, every moment of existence, unfolds within the boundaries set by that single constant. Einstein's special relativity began with the observation that the speed of light is the same for all observers, regardless of their motion. From that one principle flowed a revolution in physics. Time could no longer be absolute. Space and time were intertwined into a single fabric. Space-time that bends and stretches so that light's speed remains invariant. Moving clocks run slower, and moving objects contract along their direction of travel. The faster one moves, the more the flow of time slows, until at light speed, it stops completely. This constancy of light speed also defines the light cone, the geometric structure that separates what can be causally connected from what cannot. Within this cone lie all events that can influence or be influenced by a given point in space and time. Outside it lies the unreachable, regions forever disconnected. The light cone is not an abstract diagram. It is the architecture of reality, defining the boundaries of cause and effect throughout the universe. Every signal, every form of communication, must obey this limit. No information can travel faster than light, for to do so would reverse the order of cause and effect. Time itself would unravel. This rule ensures that the universe remains coherent, that history flows in one direction, and that events unfold in consistent sequence. The finite speed of light also explains why we live perpetually in the past. When we look at the moon, we see it as it was 1 second ago. When we gaze at the sun, we see it as it was 8 minutes ago. The light from the nearest star takes more than 4 years to reach us. The most distant galaxies show us the universe as it was billions of years in the past. The observable cosmos is, in truth, a vast time machine made of photons. Light's constancy also governs motion itself. As an object approaches the speed of light, its energy grows without bound. It can accelerate forever and never reach light speed, because doing so would require infinite energy. This rule divides the universe into two domains: those that move through space-time slower than light, and those, like photons, that move through space-time itself, for whom time stands still. This limit shapes everything from the orbits of planets to the operation of satellites. The global positioning system, which guides billions of devices, must correct for both the slowing of time due to motion and the warping of time due to Earth's gravity. Without these relativistic adjustments, it would drift kilometers off course each day. The finite speed of light is thus not a restriction, but a foundation. It binds together space, time, and causality into a single, consistent order. It defines not just how fast we can travel, but how the universe can exist. Light speed is the heartbeat of reality, the pulse that synchronizes the cosmos. At the edges of space-time lie regions where light itself falters, where gravity grows so strong that nothing, not even a photon, can escape. These are black holes, the most extreme manifestations of Einstein's theory of general relativity. They are not objects, but regions of geometry, where space-time curves inward so steeply that all paths lead to a single end. A black hole forms when a massive star exhausts its fuel and collapses under its own gravity. If its remaining mass exceeds about 3 times that of the Sun, no known force can halt the collapse. The result is a singularity, a point where density and curvature become infinite, hidden behind a boundary called the event horizon. Beyond that horizon, escape is impossible. From the outside, a black hole's most striking feature is its shadow, the event horizon. Telescope's image of the black hole in Messier 87 revealed a glowing ring of light bent by gravity around a dark center. That ring is made of photons orbiting the black hole near the photon sphere, tracing the exact geometry predicted by Einstein a century earlier. But black holes do more than trap light, they reshape it. To an external observer, any object falling toward a black hole appears to slow and fade, its light redshifted to oblivion. Yet to the falling object itself, the plunge proceeds normally, with no sense of crossing a boundary. Time flows differently for each perspective, revealing how gravity and time are inseparable. Stephen Hawking's insight added a quantum dimension to this story. Quantum fluctuations near the horizon can produce pairs of particles, one escaping while the other falls in. The escaping one becomes real, carrying energy away. This process, known as Hawking radiation, means that black holes slowly evaporate. They are not eternal prisons, but temporary structures, radiating faintly as they lose mass. This radiation gives black holes a temperature and entropy, linking them to thermodynamics. Their entropy, proportional to the area of their horizons, measures how much information they can contain. This realization led to the holographic principle, the idea that all the information within a region of space can be described by data stored on its boundary. In that sense, the universe itself may be a kind of hologram, with reality emerging from information encoded on surfaces. Black holes, once symbols of destruction, have become laboratories for unification. They connect gravity, quantum mechanics, and thermodynamics in one framework. They show that light, information, and space-time are interwoven. Even in the darkest regions of the cosmos, light remains present, bent, delayed, transformed, but never truly lost. At the deepest level, the universe is made not of particles, but of fields. Every force, every form of matter, every bit of radiation arises from these continuous entities that fill all of space. The photon, the electron, the quark, all are excitations of their respective fields. Light itself is the simplest expression of this structure, a ripple in the electromagnetic field. Quantum field theory unifies the principles of quantum mechanics with relativity. It describes how particles emerge as localized vibrations of fields and how they interact by exchanging quanta. The photon, as the carrier of the electromagnetic force is one such quantum. The fields never vanish. Even in empty space, they fluctuate, giving rise to virtual particles that blink in and out of existence. This restless vacuum underlies all physical phenomena. The Casimir effect, a measurable force between two closely spaced mirrors, arises from the exclusion of certain virtual photons between them. The same vacuum energy that fills the universe may drive its accelerating expansion, appearing as dark energy on cosmic scales. The standard model of particle physics organizes these fields into a coherent framework. It explains electromagnetism, the weak force, and the strong nuclear force through principles of symmetry. Light, represented by the photon, is the mediator of one of these fundamental interactions. Even mass itself arises from interaction with another field, the Higgs field, which imparts inertia to otherwise massless particles. Light alone escapes this influence, remaining pure energy, traveling forever at nature's speed limit. This understanding transforms our view of reality. Matter and energy are not separate substances, but expressions of the same underlying fabric. The photon, in its simplicity, is not an exception, but a prototype, the archetype of all quanta. Its existence proves that the universe's most complex structures emerge from the vibrations of invisible fields. Light, therefore, is not something that moves through space. It is space in motion. It is the geometry of the universe made visible, the rhythmic pattern through which reality expresses itself. For most of human history, our understanding of the universe was limited to what the eye could see. But the visible spectrum is only a tiny fraction of the electromagnetic field. Once scientists learned to detect wavelengths beyond human perception, the universe transformed from a static collection of stars into a dynamic, evolving cosmos rich with hidden structures. Infrared light reveals the heat of forming stars buried within clouds of gas and dust. Ultraviolet light shows the fierce radiation of young, massive stars that shape their galaxies. X-rays and gamma rays uncover the universe's most violent events, colliding neutron stars, supernova explosions, and matter spiraling into black holes. Radio waves trace the vast structures of galaxies and the faint afterglow of the Big Bang itself, the cosmic microwave background. Each wavelength carries its own story. The cosmic microwave background, discovered in 1965, is light from the universe's earliest moments, stretched into microwaves by cosmic expansion. Its faint ripples record the first imprints of structure, the seeds of galaxies and clusters that would form billions of years later. Through spectroscopy, we have learned that every element in the cosmos leaves a distinct fingerprint in light. The composition of distant stars, the motion of galaxies, even the presence of planets around other suns can be read through these patterns. Light has become not just illumination, but information, the universal messenger that carries the memory of everything that has ever happened. Modern observatories, like the James Webb Space Telescope, extend our vision deeper into time, capturing light that has traveled for over 13 billion years. At the same time, detectors on Earth and in orbit observe photons across all frequencies, transforming the sky into a vast multi-wavelength map. With each new range of light, we peel back another layer of the universe's hidden architecture. And yet, for all its reach, light remains our only window into the unknown. If extra dimensions, dark matter, or new physical laws exist, it will be through light, through its bending, scattering, or delay, that we will first detect their presence. Every discovery, from the nature of atoms to the shape of the cosmos, has come through the patient decoding of light's messages. In the end, light is more than a phenomenon. It is the foundation of perception, the measure of motion, and the key to understanding existence itself. It defines the limits of knowledge, yet continually expands them. From the quantum to the cosmic, it binds the universe into one continuous field of information. Through light, we have mapped the visible universe and glimpsed the invisible. It reveals not only where we are, but what reality is made of. And as long as light continues to travel across space, across time, across thought, the search for truth will never end.